Okay, welcome to this online course on Lie Algebras in particle physics. The setting is slightly different from what you're used to and what I'm used to. Teaching from my attic is not a thing that I'm very much used to doing, but we have to make do with the current situation. So let's just get started. So the course is titled Lie Algebras in Particle Physics. This is a bit of a narrow title, perhaps. We could also have called this course Symmetries and Group Theory in Physics. But certainly an important application of group theory in physics occurs in particle physics. So in the courses on quantum field theory and the standard model, knowing something about the groups involved in the gauge theories, the Lorentz invariants, will be very important for you. So this first video will essentially deal with chapter 1 of the lecture notes. What am I going to do now is I'm going to give some motivation for studying groups and symmetries. Then I'll recap the formal definition of a group, which I think most of you have at least seen before, but I'll go through the details anyway. Then I'll mention some common properties of groups. And finally, give you some definition of what a representation is, which is really the way in which groups are implemented as symmetries in a physical system. Okay, so let's start. So what is a symmetry? So symmetries are really the motivation for a group, so let's be a bit more precise here on what symmetries are. For me, a symmetry is just a transformation of a system, or more kind of mathematically just a set, perhaps with some structure, that preserves something. That preserves perhaps the structure, that preserves some structure. And this can be anything. In physical systems, it could, for instance, be that it preserves the equations of motion. For instance, if I look at the classical mechanics of this wiper, and if there is perhaps no gravity, then its equation of motion will be preserved by any rotations of this object. So then the rotations are really symmetries of the equations of motion. It can also be some action. So this is typically tied to a symmetry of the equation of motion. It can be the shape of some object. For instance, here, so this is kind of a benefit of giving a lecture at home. I have plenty of material available to use as attributes in the course. So here, this Duplo piece, it is invariant. Its shape is invariant under rotations by pi over 2. So there are symmetries involved just in the shape of this object itself. If you have multiple identical particles, if you like, there are symmetries that interchange these particles, and the system will be indistinguishable if I do that. So these are also symmetries. So in general, they're just some transformation, so transformation from the system S to itself. So why are symmetries important? I'm sure you can already name a couple of reasons yourself, but let's just write down a couple more. So one very important reason, and something that you're certainly encountering, say in quantum field theory, is that symmetries help to organize degrees of freedom. Organize degrees of freedom. And how do they organize degrees of freedom? Well, you capture your real degrees of freedom of your system into objects that transform in a particular way under symmetries. And this is a very useful bookkeeping device. So, say in classical mechanics, you would, for instance, take your position coordinates xi and group them into a vector. So why is this a useful thing to do in classical mechanics? Well, it's because vectors transform in a natural way under a symmetry, which are the rotations of the system. And it also means that if you're going to write down classical mechanical laws for the motion of particles, that I really want to do that on the level of the vector and not on the level of the component, because on the level of the vector I know very well how I'm allowed to combine vectors in such a way that the equations of motion actually preserve these symmetries. For instance, for vectors, we know that if you take inner products of vectors, that they are preserved by rotations. Well, if I take arbitrary formulas, including the components of a vector, then typically they do not preserve the rotational symmetry. This is also very important in quantum field theory if you have, for instance, the standard model, which has many degrees of freedom. It has like 120 or so field components that are wiggling in your space. But it also has many symmetries. So of course it has translational symmetries, rotational symmetries, but it also has these gauge symmetries. And all these symmetries, they serve to group up these 120 degrees of freedom into multiplets. And also into vectors and under rotations. And there are far fewer multiplets than there are actually degrees of freedom. So if you want to write down a model for the standard model, which of course has been done, that's why it's called the standard model, you have to determine what kind of terms you're going to include, say, in the action of the standard model. Now, if there are 120 degrees of freedom, there is a humongous amount of terms that you would be able to write down. But if you're requiring that the symmetries are implemented in the standard model, so the gauge symmetries, say SU3 times SU2 times U1, then only very particular terms are allowed in the action. Terms that take full multiplets combined. So that's why the standard model actually only has something like 20 free parameters that you have to measure. Instead of like thousands of them, if you could take arbitrary interaction terms between these 120 degrees of freedom. So it's just a very economical way to deal with your physical system if you have organized your degrees of freedom into quantities that transform nicely under symmetries. Another reason why symmetries are really nice, for instance in classical mechanics, is that if you have a continuous symmetry, then Noether has told us that you get conserved quantities. And conserved quantities are very useful if you want to solve the equations of motion of a system. If you have enough continuous symmetries that all lead to conserved quantities, then sometimes you do not really have to solve any differential equations anymore to solve the equation of motion. You only have to solve algebraic equations. In quantum mechanics, there is a similar analogy between continuous symmetries and things that are easier to solve. And this is, okay, let me be a bit more precise about symmetries in quantum mechanics. So a symmetry corresponds to a unitary operator, say u hat, that commutes with physical observables, that commutes with operators that correspond to physical, commutes with observables. And whenever you have operators that commute, you can do all kind of fancy things like simultaneous diagonalization. And we'll actually see that if you have an observable operator O, so some Hermitian operator that commutes with the symmetry operators, that there are very stringent restrictions in the matrix elements of this operator. So if you look, for instance, at the expectation values of such an operator, then depending on kind of where the states psi live, say in the eigenstates of these unitary operators, there are stringent restrictions on what the outcomes of experiments can be, right? So these are like expectation values of outcomes of experiments of measuring this observable in that state. So we'll get to this probably next week, and what exactly these conditions are that you can derive as soon as you know that there are symmetries present. Okay, and I'm sure you can think of a couple more reasons. But what the takeaway message is here is that actually for each of these considerations, it is very important to understand kind of the algebraic nature of symmetries. Right, so here we're seeing that symmetries, they organize degrees of freedom. So we really want to make the best use of this organization. And to understand how some particular symmetry, like the gauge symmetry SU3 times SU2 times U1 in a standard model, gives rise to multiplets, I really have to understand something about how these symmetries algebraically relate to each other. The same is true for these conserved quantities. If you're in a system with many continuous symmetries, then sometimes your system is integrable, meaning that you have plenty of conserved quantities to solve the equation of motion with algebraic equations. But to understand exactly, okay, when is it enough, then again you need to know something about how these different symmetries algebraically interact with each other. And similarly here, so the precise restrictions that you can derive in quantum mechanics for matrix elements of observables, it depends on how the different symmetries in your system relate to each other. So when I say or ask about the relation between symmetries, I'm asking about the algebraic structure underlying transformations of a system. And this is exactly group theory. So a group captures the the structure that is contained in how symmetries compose. The structure contained in the composition of symmetries. And we really want to get the most out of this structure. And for that we really have to go into the abstract definition of groups and properties. So this concludes the motivational part of this lecture, and now I really want to move to the mathematics. And I'm going to start by just writing down for you the definition of a group, which I hope you've seen before, and if not, then just pay attention here. So the definition of a group is the following. So a group denoted by kind of these two elements, G and some operator, it is a set G, an abstract mathematical set G, together with a binary operator, this thing, which is really a map from G times itself to G, so it takes a pair of elements of this set and associates a third element to it. And this binary operation has to satisfy a number of axioms that I'm going to write down explicitly. The first is the closure, which is saying that if you have two elements in a group, then I really want this binary operation to be well defined. So if I take typically I'm going to call this binary operation composition or product. So if I take the composition of G and H, I want it to be again a part of the group. So you should keep in mind here that these elements of the group are going to be symmetry transformations. So a transformation is really just a map, or just some map from your system S to itself. So when I say that I'm looking at the composition of two such transformations, it means that I'm going to take the composition of those transformations on S. Right? So H gives a transformation of S, and let's say after H I do G. So typically when I have groups, I'm reading these compositions from right to left, first transforming by H, then transforming by G. So this is saying that if I have a symmetry transformation H, another symmetry G, then I can perform the symmetries consecutively, and they should again be a symmetry. Now this is certainly true for symmetries that we know, for instance rotations. I can look at the rotation around this axis, say by pi over 2, and a rotation around this axis by pi over 2. And I can look at the composition of these two symmetries, first doing this rotation and then this one. Right? So that is certainly also a rotation. Right, and some more mathematically minded students here might object that this is a bit superfluous, this axiom, because I've already required this to be a binary operation. I've required it to be a mapping from G times G to G, which of course is already assuming that the result has to be in G. But I'm going to write it here explicitly because when you're going to check that a certain set plus an operation is a group, you really have to check that this operation is well defined. So this is the closure property. The second property is that of associativity. Which expresses a natural property that we want to have when you have three such elements. So if I take three elements F, G, H in the group, then I want to make sense of what it means to compose these three elements. So in terms of symmetries, what it means to take, say, 3 rotations and turn them to 1 rotation. So I want to compose like first doing H, then doing G, and then doing F. But this is not necessarily a well-defined operation because I only have this binary operation, which takes 2 elements and then assigns a third one. So to make this a well-defined operation, I have to choose which kind of composition to do first. There are really 2 options to do here, and associativity is telling, or is requiring, that these 2 options give the same answer. So I get F, G, H. I can either first take the composition of G and H and then with F, or I can take the composition of F and G and then with H. So if this is satisfied for all elements, then this operation is called associative. The third axiom that I want to require is the identity which is saying that there exists a special element E in the group such that composing with this identity element gives the same element again. So E composed with any element G, or in the opposite order, gives the element G again for all G in the group. And finally, the axiom that we want to have is the inverse, which is saying that for each element G in the group, there exists a element G inverse in the group such that composing G with G inverse in either order gives the identity. So these four axioms, they really capture what we think of as symmetries. So let's look at the last two properties. So suppose I have rotations, then the identity axiom is requiring that there exists an identity rotation, which of course is just a transformation that does nothing. If I compose nothing with this rotation, then I get that rotation again. Or if I first do the rotation and then nothing, then that is again the same rotation. The inverse, well, clearly for rotations, if I have rotated something, I can always rotate back. So if I compose a rotation by pi over 2 with a rotation by minus pi over 2, I'm back at the identity transformation, doing nothing, right? So certainly for rotations, there is always an inverse. So what I'm going to do now is write down a couple of abstract examples of such groups which do not obviously have an interpretation as a symmetry of a system. But okay, later on we're going to see that whenever you have a group, you can always construct some system that has this symmetry as its group. Okay, let me write those examples up here. And then after we've seen a couple of examples, we can go through several properties that a group may or may not have. Okay, so some examples. So here's a very simple example. I take my set to have just two elements, say -1 and 1, and I take the binary operation to be multiplication. Okay, let's just write down the examples first and then just look, well, how they satisfy these axioms. So the other group is the integers, where the binary operation is addition. Let's look at the permutation group of a set X. Okay, so what is the permutation group of a set X? So it's the group, let's denote S sub X, a circle for the composition law, where S of X is really the set of bijections from X to itself. So this is a set of bijections psi from x to x. Let me write f. Bijection and the operation is just composition of these functions. Okay. And okay, typically we do not look at arbitrary sets where we take, for instance, x to be the set 1 up to n, the integers 1 up to n, and then this group is called S sub n. So S sub n is really the permutation group of the first n integers. Okay. And then finally, let's look at yet another type of binary operation, which is matrix multiplication. So let's take this set to be the set of real invertible matrices. So this is the general linear group of, say, m by n real matrices. So this is n times n real matrix M, and we have to make some requirement, and let's make the requirement that the determinant is not equal to 0. So it's invertible, and then the operation is matrix multiplication. Okay. So I claim that these are 4 different examples of groups. So let's quickly have a look what, for instance, the identity and inverse of these groups should be. It should already be clear that closure is valid for all of these. Whenever I multiply either 1 or minus 1, I always get 1 or minus 1. Whenever I add 2 integers, it's again an integer, so it's closed. Whenever I take the composition of 2 bijections, okay, let me write it explicitly here. So the composition of 2 bijections Fg, it is the bijection that associates to x and x the element, well, first taking the image of G and then taking the image of F, right? So whenever I take the composition of 2 bijections, I again get a bijection. Whenever I take the product of 2 matrices with non-zero determinant, I get a matrix with non-zero determinant. So it's closed. Now you can easily check that all of these are associative. The identity elements, so what are the identity elements? So for multiplication, the identity element, it should be just 1, because multiplying by 1 does not change anything. The identity for addition, well, it should be 0. Because adding 0 to anything remains unchanged. The identity for permutations, well, that should just be the trivial bijection that sends every element to itself. So here, the identity is the, let's say, the identity map. And okay, the identity for matrices is, of course, just the identity matrix, the n by n identity matrix. So clearly, these identities satisfy these relations. How about the inverse? Well, again, this is easy to determine. So the inverse of multiplication, it should be 1 over the multiplicative inverse. And luckily, these are really present in this set. So the inverse of 1 is just 1, because it's the identity. And the inverse of minus 1 is 1 over minus 1, which is minus 1 itself. Okay, so the inverse of, say, x in minus 1. 1 is really x inverse is 1 over x, okay, which in this case is just x itself. The inverse here is so x inverse is minus x, right? Because that's what I have to add to x to get the identity, which is 0. For the permutations, the inverse is going to be the inverse mapping. So inverse here is just the functional inverse. And for the matrices, it is the matrix inverse. Well, even if you have not seen this before, you could have guessed just by the terminology that this is the case, right? Inverse is just matrix inverse. Okay, so that all makes sense. And again, checking these properties is very straightforward. Okay, so now that we have a couple of examples acting on quite different types of sets, G, let's just go through a couple of properties that a group can have, and then just see where are the differences between these groups. So so we've done group definition plus some examples. Now let's look at properties. Okay, so we need a couple of definitions. So the first thing we observe is that sometimes the order in which I perform the binary operation does not matter, like for multiplication and addition, but sometimes it does. I mean, you should know quite well that if you have two matrices, that in general the order in which I multiply them does matter. And the same is true for permutations. If I have, say, if I look at S3 with 3 elements, 1, 2, 3, 1, 2, 3, and I look, say, at the permutation that interchanges the second two or the first two, then the order in which I compose these permutations is going to lead to different results as permutation. For instance, if I first do this one and then that one, then 2 will end up in position 3 because it's swapped here and here nothing changes. But if I would first do this permutation and then that permutation, then 2 would end up in position 1 and remain unchanged after this permutation. So we call groups that satisfy the requirement, or satisfy the property that it does not depend on the order, to be abelian. So a group a group is abelian if G H is equal to H G for all pairs of elements of the group. And otherwise we call it non-abelian. Okay, here's another definition. The order of a group G, denoted like the absolute value signs around G, it is just the number of elements of the set. So in particular we can have a distinction between finite groups and infinite groups. So let's just see what we have in our examples. So here we have 2 elements, so I get size 2. Here we have all the integers, so this is an infinite group. Infinite. Permutations. Well, suppose I'm looking at the set of order n, so at Sn, and I see that the order of Sn is the number of permutations of n elements. But that is just n factorial, right? N factorial. And well, the set of real matrices, n by n, well, clearly there are infinite number of them. Okay, so here we already have a couple of finite and infinite groups, and you can also see there is a bit of a difference between this last example and the integers example, in the sense that this is actually a discrete group. It is based on a discrete set, a countably infinite set, while here, I mean, these are parameterized by real numbers, so this is an uncountably infinite group, and actually it's a continuous group. So meaning that its elements depend continuously on a set of real parameters. So such continuous groups will play a very important role later on in this course, and they are exactly what are called Lie groups. And Lie groups are closely related to Lie algebras. Okay, so that's just a quick peek ahead. Okay, so let me write down a bit more what we need. So we see here quite different implementations of the group structure. But even if two groups have very different implementations, they can actually be very similar from an algebraic point of view. And to make this mathematically precise, we have to introduce the notion of isomorphic groups. So we say that two groups G, H are isomorphic. And okay, let me be also a bit precise here. So before I said that a group is really a pair of a set G and a binary operation, while here every time I'm writing just G. And this is because typically when I write down a definition of a set, there is a natural operation working on this set. So if it's clear from the context what the operation is, I'll just denote the set by the denote a group by its set G. Okay, so two groups G and H are isomorphic if there exists a bijection, say phi from G to H, such that in some sense the composition law of the groups is preserved. So that means if I take an element, if I take elements G and H in G, then I want that if I take the image of G, so that will be an element in H, and the image of H, and I compose them using the binary operation in H, that is really the same as taking the operation in G and then mapping it to H. Okay. So if two groups are isomorphic, then, well, as soon as you have identified kind of elements in the set G to elements in the set H, all the algebraic structure is completely equivalent. It does not matter whether I use the binary operation in H or in G, sorry, or in H. So really, these should be interpreted as the same groups, or these are the same abstract groups. So what we say is that isomorphic groups describe the same abstract group. So if you like, an abstract group really only contains the information of what elements compose into what other elements. But they don't contain information about, well, how they're represented in some particular way, what the symbol is that we're using for the group operation. So an abstract group, if you like, it's an equivalence class of all possible groups that are isomorphic to each other. And each kind of description, G and H, if they are isomorphic, they are an equally valid description of an abstract group. Why is this useful? Well, I mean, just going by these examples, it's clear that you can write down infinite number of different groups, infinite number of different description of groups. But as soon as we restrict ourselves to abstract groups, then, for instance, at each order, if we fix the order of the group, there is only a finite number of different abstract groups. So if you're interested in classifying groups, which in turn classify the symmetries in a system, then it's important to just kind of restrict your attention to abstract notions. Okay. So in the exercise session, you're going to look at 3 different descriptions of the same group. So let me just write them down here. So exercise, you will be looking at the cyclic group of order n, and we'll give 3 explicit definitions of this. The first one is saying that we're using Cn, which are the integers 0 up to n minus 1, with addition, where we view the addition as modulo n. So addition modulo n. But one can also look at Cn, which are permutations that are cyclic together with composition. So Cn is really a subset of the permutation group of cyclic permutations. So cyclic meaning that, for instance, if we look at 5 elements, that you're looking at permutations like this, or compositions of such permutations. And the last example is this one, where now I'm going to use complex numbers, so Z in the complex plane, requiring that they are nth roots of unity together with multiplication. So I claim that these 3 groups are all isomorphic to each other, and your task will be to find the explicit isomorphisms. So each of them is an equally valid definition of the abstract cyclic group of order n. Okay. So these are, for now, the most important properties that we need. Let me get to the final part of this video, which is about representations of groups. So representations are really going to be the mathematical definition of how a group can act on a system as a set of symmetries. So definition: a representation D of G on a vector space V is a map D from the set G to the general linear transformations on V. So that means that for each group element in G, an invertible linear transformation dg of V. And these have to satisfy some properties, satisfying that if I take two group elements, then both should give a linear transformation of V, which I can therefore compose, and the result should be the same as taking the linear transformation associated to the product of these two group elements. So this is what we call a representation. Let me add to that the dimension of D is, okay, you denote that dimension of D, it is really the dimension of the vector space on which we're working. Okay. So here, when we have a representation of a group, we explicitly get a transformation of a system. And in physics, this system, it is going to be encoded by some linear space. So every group element describes a transformation of our linear physical system. So typically V, so if V has like n dimensions and we've chosen explicit bases, they can either be real or complex, then of course these general linear transformations are just matrices. Then dg is a n by n matrix, which is either real or complex depending on your vector space. So a representation is just a way of taking the algebraic structure in your group and turning it into a set of matrices, so one for each element. And these matrices have to be such that taking the composition in the group is equivalent to just multiplying these matrices. Okay. So finally, I need just a bit more before we stop. I mean, whenever I have a representation, I can get another representation by slightly changing the bases in my vector space. And since at some point we want to classify representations of a group, we want to take out this redundant information. So to this end, we say that two representations D and D prime of G are considered equivalent. So this is denoted with this wiggly equal sign, D equals D prime, if there exists a similarity transform. So really a change of basis of your vector space V, similarity transform right, so this is a linear mapping, from V to V prime. That has to be invertible such that if I take this linear transformation on V, then I'll take the image to V prime, and okay, I want this to be now a mapping from V prime to itself, so I have to put an S inverse on the right hand side, and I want this to be exactly the representation D prime for all G in G. Okay, I mean, this is the transformation that you expect when you just choose a different basis in your space. Then an S will then be exactly your basis transformation matrix. Okay. So with this, we can kind of finish the introduction, and I want to sketch for you a picture of what the goal is going to be. So we have some set of symmetries on our physical system, symmetries on our system that we're interested in this system. And what we've seen is that, okay, there is some algebraic structure that I can extract from these symmetries, algebraic structure, and they encode an abstract group. And then to go back, if I have some explicit abstract group, I can ask also how can it be implemented as a symmetries of a system. Well, that's going to be through this representation. Now here I'm kind of making the assumption that this system is actually a linear system, such that there is always, I can always multiply the elements of my system by some real number. Now this is not much of a restriction on physical systems. For instance, any quantum mechanical system lives in a Hilbert space, which is a linear space. But even in cases like in classical mechanics, where there is no clear linear structure, typically there is some way to kind of change your coordinates in such a way that it does become a linear space. So in general, we're really going to look at abstract groups that act like symmetries on a linear space. And why is this useful? Because in some circumstances, one can actually classify all groups with a given properties, and one can also classify all its inequivalent representations. So as soon as one has classified both of these, then one has classified all possible ways that symmetries can act on a physical system. And one can derive properties about these symmetries on the level of the abstract group, and the consequences of these properties will hold on any system that has such a representation of that group. Just to give you one example, the rotation group in 3 dimensions, it acts, for instance, on, it has an abstract group, which is the 3-dimensional rotation group. It acts, say, on the hydrogen atom. So if I have an electron that goes around the hydrogen nucleus, now the fact that it has a symmetry group has some consequences, in particular that the energy levels of this electron are degenerate, and it has certain quantum numbers, like the angular momentum in the z direction and the total angular momentum, that completely specify the state of this quantum mechanical electron. Which, I mean, this abstract group we can actually find within a classification we're going to do. But then we're going to notice that this abstract group, it also appears in systems that are not just have a rotational symmetry. For instance, if we look at particles that transform within the weak force multiplets of the standard model, they have what is called a isospin symmetry, which is an abstract internal symmetry, but it turns out to have exactly the same abstract group as the rotation group. And that also means that the different quantum numbers one can derive for this isospin symmetry are going to be exactly the same as those for the rotational symmetry in the hydrogen atom. So one does not have to do the whole kind of exercise again of determining what are the eigenstates of this system. One just takes the results of the group theory and export them to the particular system that you're looking at. Okay, so this concludes the review of chapter 1 of the lecture notes. And in the next video, we're going to continue looking at representations of finite groups.